All right, so today, this is Physics 1C for Tuesday, May 11th. This is tidal inductance, and we may or may not get to that topic today, but we'll see. We should. Okay, so this is what we're talking about today. We're not talking about superconductors. We talked about that earlier. So we're going to be talking about induced electric fields. This is related to Faraday's law. Then we're going to talk about displacement current, which is a modification of Ampere's law. And then once we've done that, we're going to have all of Maxwell's equations. And we'll discuss those. And then if we have time, we'll go into discussing what inductance is. We'll probably get to here. And then that'll be all we can really cover for today. Okay, so the first topic is induced electric fields. Okay, so we're going to start with the setup that's right here. And since it's already drawn, I'll take some time to describe what's happening. Okay, so let's read the little footnote right here. Caption. The windings of a long solenoid carry current I that is increasing at a rate of DiDT. The magnetic flux in the solenoid is increasing at a rate of d phi b dt, and this changing flux passes through a wire loop. An EMF of this is induced in the loop, inducing a current I prime that's measured by the galvanometer. And there's a cross-sectional view. So what we have here is a solenoid. So here's the blue kind of core of the solenoid. That blue core could be, I don't know, a paper towel holder, or it could just be like a piece of iron. If you have a piece of iron in here, it's going to increase the ability to generate a magnetic field. It'll generate bigger magnetic fields if you have iron there instead of air, for example. Around this, we have a coil that's wrapped like this, which means the current's flowing down on this side and then up around this way, out that way. It says that the current through the coil is increasing, which means there's going to be a flux through this ring out here. The ring is just a wire loop, the gold ring right here, and it has a galvanometer on it. Now, what we learned in the last chapter, or this is the same chapter actually, is what's called Faraday's Law, which says that you're going to have an EMF induced that's going to be equal to negative N times the rate of change of the flux. I don't know why they bother to put all these equations inside the caption here, but regardless. And that we could find the amount of current that gets generated inside of this loop right here, which they're calling I prime, by taking that induced EMF and dividing by whatever the resistance of the coil is here. So R is going to represent the resistance of this coil that has a galvanometer in it. A galvanometer basically is just something that measures current. So this thing just measures current. So we've looked at systems like this before. It's very similar to a problem that we did on Thursday, where we had a ring and we had a solenoid and we had to calculate the EMF induced in the ring, right? So that problem is kind of a nice lead-in to this problem, because if we want to describe what's happening in the ring on the outside, then we can look at it from this perspective over here, where what we're looking at is the current you can see is flowing around in a circle like this. That means that we're viewing this, I believe, from this end over here. Does that seem right to y'all? If we look at it from this end, this is what it's going to look like. Do you agree with that statement?
Yeah. Yeah.
Okay.
Yeah.
Magnetic field's going into the page, right? Which is this way. So that hopefully makes sense. Now, what we want to say is that if we know that there is a current that's induced in our loop, and I'll go ahead and draw it on here, that current is called I prime up there, right? That's our induced current, I prime. And notice that the direction of that induced current is opposite to the direction of the current in the solenoid. Why is that?
Flux is increasing.
Yeah, increasing flux means that the induced EMF has to point basically opposite, which means the current has to go opposite, since it's a ring around the other object. Okay. Now, if you think about what's going on then, imagine that you're a positively charged particle inside of here. If there's a current flowing in that wire, right, then that means that there must be an electric field in the wire that's pushing the charges along. After all, that's what makes things move. So we know that because there's a current I prime, there also has to be an electric field, basically kind of like a circular electric field here, right, that points around like this. And the electric field is labeled as E. And as you can see, all the electric field vectors are basically tangent to the path. In addition, what we're going to prove now is that all of the electric field is uniform within here. So let's go about doing that. So what we're going to need to do is we're going to need to go back to an equation that we had early on about potential difference. So electric potential difference, delta V, we said was equal to the negative integral of E dot dl. And remember that EMF and potential difference are basically the same thing, right? So what we can do is we can basically make these two equations equal to each other. We can say, since this is basically the same thing as EMF, that we can just write that negative integral E dot dl should be equal to negative capital N d phi dt. We can kind of ignore these negative signs now. And the problem that we're doing right here, capital N is 0, or is 1, sorry. So we'll just go ahead and plug that in. N is equal to 1 in this problem. There's just one ring out here, right? All right. Now there's some things that are labeled on here. What's labeled? So this area is A, and then this radius is R. Okay, those are the only variables that we have here. So now what we want to do is we want to find what the value of the electric field at the location of this wire would be. What's the electric field inside the wire? That's our goal here. And we're going to refer to that as an induced electric field. So what we really need to do is we really just need to isolate this term right here, right? Okay, so in order to do that, we are going to say, well, this is now just a 1. For the flux now, this is going to be the magnetic field of the solenoid multiplied by the area of the solenoid A. That's what the right-hand side equation is going to be, just B times A. And we learned in previous chapters that the magnetic field of a solenoid, that's this B, by the way, the magnetic field of the solenoid is going to be equal to mu naught times the number of turns per unit length of the solenoid multiplied by the current flowing in the solenoid. So this then is going to be equal to, I'm not going to skip any steps because this is probably complicated enough as it is. So we put the mu naught, little n, I. This is the number of turns per unit length in the solenoid area. Now, for the left-hand side, what we're going to do is we're going to say that if we were to draw some dl vectors on this picture, they would be little line elements that would be parallel to the circle, or sorry, tangent to the circle, but parallel to the electric field. That means we can rewrite this as just the integral of EDL. The next thing we can say is that because of the kind of symmetry of this problem, it has rotational symmetry. It's hard to believe that any of these electric fields should be different from each other. Does that seem reasonable to everyone?
Yeah.
That it should be the same everywhere, because if you think about it, what you could do with this ring is, like, here's the galvanometer on top. I could rotate that ring where the galvanometer was like over here, right? I could rotate it like 45 degrees, or what is that, 90 degrees to the left. And you don't really change the system at all, right? And I could rotate it again 90 degrees, and you don't really change the system at all. That kind of implies that the electric field kind of has to be the same throughout here, because each part is the same distance away, right? It's a circle, so it's all the same distance. So if that's the case, then the electric field's not going to change as we move along here. The angle between E and DL doesn't change, so we can just pull the electric field out. And this just ends up becoming the electric field multiplied by 2 pi r. Okay. And then what we can do is we can rearrange the right-hand side, because mu naught, the number of turns per unit length of the solenoid, and the area are all going to be constants. And then DiDT is the one thing that's changing. We were told in the problem, it's not a problem, right? But it says that the current I is increasing at a rate of DiDT. So we have this value DiDT that we want to throw in here. And then we actually get an answer. So we get that the electric field at the location of that wire is equal to mu naught in a DiDT all divided by 2 pi r. And that's the answer. Now, it's not a simple answer, but it is an answer that allows us to say that when you have something like a solenoid that has an increasing current, it is going to generate a change in magnetic flux, and because it generates a change in magnetic flux, it actually generates an electric field in the region around it. What we could do is we could basically remove the wire and then say that electric field is there, right? Does that make sense? That around this coil of wire that has current flowing around like this, there are electric field lines that are concentric around this, basically. And they have this value. So what we could do is we could say, okay, here's my solenoid. I'm going to draw a little bit smaller here. It has flux going in, right? Magnetic field going in. We just found out that that generates electric field lines that go around in a circle around this. Now, the strength of the electric field gets weaker the farther away you go, because the only real variable in this equation is R, right? A is the area of the solenoid, this is the number of turns per unit length of the solenoid, and everything else is just a constant. Perhaps DiDT is not a constant, but the electric field itself is going to fall off as 1 over R, basically, as you move away from this. But you're going to get these nice concentric electric field lines. So that's kind of a nice representation of the way in which magnetism and electricity are related to each other, right? Because I can draw another picture that looks a lot like this, but instead of having a magnetic field on the inside, I can put an electric field on the inside. So just to show you kind of the connection, what I could do here is I could say, suppose that I take a current that flows into the page like this, right? This produces magnetic field lines around it, right? What do the magnetic field lines look like?
Concentric rings.
Exactly like this, right? And in this case, they go the other way. So this one would have magnetic field lines that go around it that are rings. And if you think about it, they fall off as 1 over R, because in this case, these are magnetic field lines, and we know that the value of the magnetic field is mu naught I divided by 2 pi r. So the equations even look almost exactly the same if you think about it. They both have a mu naught. They both have a 1 over 2 pi r. The only difference is this one has an I and this one has an NA DiDT in it. Which, if you think about it, the units of that NA DiDT have to be the same. No, they're not the same, because one's electric field, one's magnetic field. So yeah, these would have to be different anyway. But yeah, there you go. There's a nice, really simple connection between the two right there. Now we can generalize what we've done here if we go back to this line, I guess this line right here. Because pretty much what that line tells us is that if I have an induced EMF, that the value of that is going to be, if I take the induced EMF and I divide by 2 pi r, that's what I mean to say, that the value of this is going to give you the electric field. So we did this for a solenoid, but in general, you can find the magnitude of your electric field just by doing this. You use Faraday's law to find this, right? Use Faraday's law to find the EMF induced, and then you just divide by 2 pi r. That's it. That's all you gotta do. This is the answer we get for a solenoid, but it really is just the EMF, mu naught in a DiDT, right? That's everything that came from here, divided by 2 pi r. It's pretty simple. We're gonna look at a couple applications of this, but does anyone have any questions?
It's interesting how they act kind of like in this orthogonal nature with each other.
Yeah, exactly. Okay, so the next thing we want to do is to actually talk about what kind of electric field this is, because this electric field that's produced here is actually quite a bit different. So I want to remind you of something that we learned early on in this class, which is, suppose that I take a battery and I connect it up to a resistor. So we have a really simple circuit. Okay. Now, one thing we know is if I take 2 points, such as between here and here, let's say A and B, I can say that delta V between points A and B, which the way your book calls it is like the potential of point B relative to A. I can say delta V is basically given by this expression, integral E dot dl. And there's a negative sign. And then I could say, okay, well, between these 2 points, right, there's an electric field in this wire, and it has to point this way because that's the direction the current would flow, right? We know the current's flowing around this way because this is the positive side and the negative side of the battery. So if I were to do this integral, then I would get that delta V between these 2 points is some value, right? And it's going to have a number, right? Like maybe it's equal to, negative 5 volts, okay? That's what it would be equal to. If the EMF down here was 5 volts, then point B relative to point A would be negative 5 volts, right? Does everyone agree with that?
Mm-hmm.
Okay. What happens if I go between the same points? So in this case, I basically was going from point A to point B, right? What would I get if I did delta V and I instead went from point A all the way back to point A?
We should get 0.
You get 0, right? Because that's like asking the question, what's the elevation of the tabletop relative to the tabletop, right? It's 0. If you call the tabletop to have an elevation of 0 and you ask what the elevation of the tabletop relative to itself is, the answer is 0. Same thing here. If I want to find the potential of point A relative to point A, the answer is 0. Or put it another way, if this point has a potential of 5 volts and this point has a potential of 0 volts, well then if I do 0 minus 5, I get negative 5. But if I go all the way from 5 volts all the way around the circle one time back to here, you get 0 because it's 5 volts minus 5 volts. Or you can just think of Kirchhoff's rules, right? One of Kirchhoff's rules says that if I sum delta V around a loop, you get 0, right? Okay, so we call these type of electric fields here, we call that a conservative field. A conservative electric field. And we use the word conservative because it's a conservative vector field, right? It obeys this property. That's pretty much what conservative means. But it means that the work done by the force is independent of the path, basically. Now, if we apply the same concept to what we just found here, to this electric field, do you all mind if I get rid of some of these things that I've drawn on here? If we now apply the same concept to this electric field right here, what do we get as an answer? So now what we do is we start from here. Let's say this is our point A, right? And we go in a circle around this way, right? Now what do we get? Now, if we do the integral of E dot dl around a closed path, which is exactly what we did down here. This is technically the negative integral around a closed path of E dot dl. Down here what we got, whenever E was a conservative field, we got 0, right? What do we get here, though? Here, we get this. When we do the integral around E dot dl, we now get an answer that's equal to E, the EMF. So this electric field here is what's called a non-conservative electric field. I'm going to write NC down here. So it's a non-conservative electric field. So what this means is that when I produce an electric field using charges, like electric charges, like in the case of a battery that separates charges, I produce a conservative electric field. When I produce an electric field using Faraday's law, using changes in magnetic flux, you produce a non-conservative electric field. One when you do the integral around a closed path, you no longer get 0. You get E. You get the EMF. Does that make sense?
Yeah, yeah, you would totally, if you're trying to push a charged particle in that path, it's not going to be like any easier if you're kind of coming around the other way. Yeah, you would have to still do work on it.
You're saying that if we go in the same direction from point A around to point A, the field has done work, obviously. But if you go back the other direction, you're saying basically you need to do the kind of the same amount of work to go back the other way. Is that what you're saying?
Well, yeah, that looks true. That seems true. I was saying if you're just going one direction, it's not going to be like, it's not like gravity where I could like, if I lift my hand in a loop, like it's hard going up, and then it kind of, it gets
easier
quote
coming down.
easier coming down.
Yeah, to compare it to this picture down here, one thing I could do to kind of drive the point home is if I draw the electric field inside of the battery here, it actually points this way. So what happens here is that if I imagine you're a positive charge and you're sitting right here, and you go through the battery, because the battery is also going to apply a non-electrostatic force from the chemicals to lift charges from this point to this point here. Once the battery has done the work of lifting the charge from the negative side to the positive side, now the charge is naturally going to fall around the circuit back to this location, right? Because once it gets to here, there's an electric field inside the wire. Does that make sense? And that electric field inside the wire is going to naturally carry it the rest of the way until it gets back to here. And then it gets to here, and normally it wouldn't be able to climb past the battery because there's an electric field there. But what the battery does is it pulls positive charges from this side over to this side over here using chemistry, right? And it gets it past the uphill part and back to the downhill part. So it's like you go uphill and then back downhill, and you go uphill and you go back downhill, right? That never happens over here. If you go in the same direction here, you're always going downhill. If you think about it, right? You're always going downhill. That's kind of hard to imagine, right? Imagine a hill that just never ends. But that's kind of what this path describes. And if you're going the other way, if you're going in the opposite direction of the current, so you're a little positive charge in here and you're trying to climb in the opposite direction of the current, it'd be like climbing up a hill that never ends. I think that's right. Does that seem right to y'all?
Yeah, it's like but
I mean, the field is always... Go ahead.
I was just saying, like, kind of hard to wrap my head around it, but
yeah, I can draw it in a way that maybe easier to understand. I don't know. So the non-conservative field, you can't draw this with straight lines, can you? I mean, I guess you can imagine as long as you can. Is there a way that we can draw a vector field with straight lines that's non-conservative? I don't know. Can we?
Well, that's an interesting question.
I mean, I'm just thinking about if this is like the gravitational field of the planet, right? We know the gravitational field of Earth is conservative. It's pretty
maybe on a Mobius strip.
Maybe
on
a Mobius strip, yeah. Yeah, a normal field is one in which, if an object falls down to some point and you take it and you lift it back up to here, it'll naturally just keep falling down like this. Yeah, I don't think you can compare this to a straight field. Actually, now that I think about it, I was trying to say it's like a gravitational field that goes down forever, but it's really not like that. It's really quite different. The other thing to say about a non-conservative electric field is that non-conservative electric fields cannot be produced by point charges. They can only really be produced by magnetic flux, changes in magnetic flux. Because there's no way to produce a circular electric field like this just using point charges. You can try to do it yourself if you want to. I mean, as soon as you start thinking about it, I think it's really easy to understand why this is true. But in any point charge that I place down, automatically has field lines that emanate from it like this, right? So how could you produce an electric field like this? I mean, could you just take positive charges and place them in a ring? Would that do it? Not really, because now the electric field lines, you could imagine I can draw one set of electric field lines that basically goes from here to here. The problem is that there's an electric field line from this one that goes back this way. So then you might say, okay, well, maybe we put a negative charge in here. So now I put a negative charge in here. And then now you can imagine, okay, this field line goes from this to this. So at least between these two, that seems to work, because the field lines for the negative charge are going to point kind of toward the negative charge like that, right? So in between here, it looks like, okay, I've got this nice field that's kind of going in a circle. But then as soon as you get to the other side, right here, now the field lines go this way and this way. So they've kind of reversed, right? So maybe you try to put another negative charge here, but then that's going to have the same problem as when we had two positive charges together. So you just cannot produce these circular electric field lines using point charges. It just isn't possible. It just isn't possible. Okay, does this all make sense? I know this stuff is really tricky. I mean, Physics 1C, it's pretty difficult stuff, and I'm just doing my best to try to present these ideas, hopefully in a way that you can understand. To just kind of summarize what we've done, though, we looked at a solenoid. We analyzed it just as using nothing new, just using equations we've learned in the past week, as well as our definition of voltage, of EMF. And what we did is we found that when you have a change in magnetic flux, you actually produce an electric field that falls off as 1 over 2 pi r, as 1 over r, and the size of the electric field is given by taking the induced EMF and then just dividing by 2 pi r. And the units for this work out because the units of EMF are volts and the units of electric field are volts per meter. And then the other piece of it is that these are non-conservative fields. Okay, so let's look at some problems. I think this is the one to start with. And then here's a little more, I think this one's a little harder. It's not that much harder. Okay, this one refers to this picture, I think, 29.18. So let's copy this. And that way we'll have it for this problem. Whoops. They got stuck together. I just want to click U, cut, paste. All right, so it says, suppose the long solenoid has 500 turns per meter, so that's little n. I'm not going to write turns because turns isn't really a unit. A cross-sectional area of 4 centimeters squared. That's going to be, what, 4 times 10 to the negative 4 meters squared. The current in its windings is increasing at a rate of 100 amps per second. Okay, so that's the rate at which the current is increasing, and that's what we call DiDT. It says find the magnitude of the induced EMF in the wire loop outside the solenoid. So the first thing we're going to do is find the induced EMF here. That part's pretty easy. We've done these kind of problems in the past. So the induced EMF is given by negative N times d phi dt. Our magnetic flux in this case, so N is 1. N is the number of turns in the coil that's having the current induced in it. So it's negative 1 times ddt of, we need to plug in here B times A B is equal to the magnetic field of a solenoid, so mu naught times little n times I. And then we just pull everything out except for the current. And I think we have all of the things we need to plug in now. We're not going to worry about that negative sign because the negative sign comes from Lenz's law, and we've already drawn the direction of the current on here. So for this, we're going to get 4 pi little n is 500 inverse meters. Area 4 times 10 to the negative 4. Did I do that conversion right? Do you all agree with that?
Yes, yeah.
Mm.
Okay. So then we get this equation. Plug this into a calculator.
I got 2.5 to the negative 5.
And that's going to be in volts. 25 microvolts. Okay, let's see. 10 to the negative 7.
That's what I got too.
10 to the negative 4. Okay. Okay, part B. Part B says, find the magnitude of the induced electric field within the loop if its radius is 2 centimeters. So, if this radius right here is 2 cm, then in order to find the electric field, the magnitude of the electric field, we just have to take the induced EMF and divide by 2 pi r. That's one of the equations we just derived. Right here. What I love, one thing I really like about electricity and magnetism is that a lot of the theory is really complicated, but the equations are really easy to use. I mean, I think they're easy to use, probably because I've just been doing this for a while, but like, I mean, this equation is really quite simple. Even though it has a derivative in it, you just replace this with b times a, and then, you know, it just ends up being this just a really straightforward calculation, right? You don't even have to do a derivative most of the time. And this one's even easier. You take this number and divide by 2 pi r. You know, I think it's hard to like.
Pretty intimidating on the outside.
Exactly, it's intimidating like from the outside looking in, but once you learn what all of the languages, what all the like terminology, vocab, all that stuff, and then what the equations say in words, right? Like this just says a change in magnetic flux produces an EMF, and as long as you know what those words mean, then it's not a complicated equation. Now, that doesn't mean that like the stuff we were doing super early on was easy, but I hope by now that this stuff seems easier to you, because even though this is probably one of the trickiest chapters, it's also really fascinating. There's a lot of really cool stuff in here. So, all right, 2 times 10 to the negative 5 volts, divide by 2 pi, times the radius. We're using a radius of 2 centimeters, so that's 0.02 meters. Okay, what do you all get if you do that calculation?
B to the negative 4.
Yeah, 2 to the negative 4.
2 times 10 to the negative 4?
Yep.
Mm-hmm.
Okay, and that's going to be in volts per meter. So you can see this is a pretty weak electric field. And ultimately, the main thing that's going to control how strong this electric field is, I mean, you could use a smaller radius, but 2 centimeters, that's pretty small, right? I mean, 2 centimeters is a very, very small distance. So you're pretty close to the solenoid here. About as close as you could possibly be without being inside the solenoid, because the solenoid is 4 centimeters squared. What does that mean its radius is? Let's see. What's the radius of the solenoid? So if we take 4 centimeters squared and divide by 2 by pi, and then take that, what is going on? Oh, I'm in some kind of weird hex unit thing. What's going on?
The radius is like 1.13.
Yeah, 1.13.
Okay. Oh man, I can't get my calculator out of hex mode. How did I ever switch it? Okay, it doesn't matter for now. I'll do it later.
Hexadecimal?
Yeah.
Your calculator has that? What the heck?
I don't know. I mean, your calculator probably does too. Most TIs do. This is just a Android calculator. It's like the one that came with my phone. It's nothing special. Okay, so there's our electric field. That's it. Pretty easy problem. In fact, it's not really so much a problem as it is plug numbers into what we just derived, right? Like I don't really even consider this a problem. So I grabbed one more problem because this one actually requires you to think a little bit more. Okay. So this problem is from a different textbook, but you are going to see problems like this from your text as well in the homework. And on lab manual, I know there's a problem like this in the lab manual. Okay. Within the green dashed circle, shown here, the magnetic field changes with time according to the expression B equal to 2t cubed. I'm going to write this over here so it's easier to read. So B is equal to 2t cubed minus 4t squared plus 0.8, where the units of 2, 4, and 0.8 work out so that this entire thing gives you Teslas, and t in seconds. The radius capital R, so if you can see here, R is the radius of basically the extent of where the magnetic field is. That radius is, okay, no, it's not little r, it's big R. So that radius is 2.5 cm. It says when t is equal to, so at t equal to 2 seconds, we want to calculate A, the magnitude, and B, the direction of the force exerted on an electron located at point P1 here, which is at a distance of R1 equal to 5 centimeters. So little r1 is 5 cm. This is R1 right here. From the center of the circular field. And then the other thing we want to figure out is at what instant is this force equal to 0. So the idea is that we're going to place an electron right here. Right? An electron? Yeah. We're going to place an electron right here. We put an electron there. And the question is, what is the force on the electron? So just to remind you, or maybe you all can tell me, if I know what the electric field is, how do I find the force if I know what the electric field is?
Just multiply by the charge.
Yeah, we're just going to multiply by the charge of the particle. In this case, our charge is equal to negative electron charge. So our force is going to be equal to negative E times the electric field. Which means that if we can find the electric field, then we'll basically be done. We just take the answer that we get for the electric field and we multiply by the electron charge. So that's our strategy here. Now, does anyone have any questions before we get started? Okay. So, there is a possibility it can have a magnetic force too, by the way. So in general, I'm just going to write this down here. I think there's enough room. We sometimes call this the Lorentz force law. Or just the Lorentz force. I think this is what this is usually called. This combines together the electric field and the magnetic field force together. So Q times E gives you electric force, and V cross B times Q gives you magnetic force. So you add them together and you get what's called the Lorentz force, which just combines both of those together, right? What would the magnetic force on this particle be in this case?
It should be 0.
Why is it 0?
Velocity is 0. It's not moving.
It's not moving. Yep. The velocity is 0, so the magnetic force is 0. And in addition, if you look at it, if we can believe that the magnetic field is only confined to this region right here, this electric field, this electron, isn't even in a magnetic field, right? It's just not even in a field. So just to be completely clear here, we are talking about an electric force on an object. And the force is coming from the fact that the flux is changing, which is going to produce an electric field, which is kind of exactly what we just learned. All right, so to find the electric field, the first thing we want to do is to find the induced EMF, right? And to do that, we say the induced EMF should be equal to negative n d phi dt. So negative 1. There's no turns. Again, this would be the turns in a wire that would be out here. But there are no turns. And there's not even really a wire, right? We're finding the induced EMF basically in free space out here. So then we have DiDT of the magnetic field, which is a function of time, multiplied by the area. In this case, this area is going to be the area of the inner circle, because that's the only place where you have flux, the only place where you have magnetic fields. So this is going to be negative. So the area A here, let's get rid of this negative sign. It gets really annoying. We don't need to write induced every single time too, right? Okay, so the area A is going to be the area pi big R squared, because that's the place where the magnetic field is, multiplied by DdT of our magnetic field function, which is given right up there at the top, 2t cubed minus 4t squared plus 0.8. Now we know we're going to be finding this at t equal to 2 seconds, but we can't plug in t yet. We got to take the derivative first, right? I guess it's okay to plug in r since we have all the... Yeah, let's wait. Let's plug in the values at the end. Okay, the derivative of this, what is it? 6t squared minus 8t 0. So our induced EMF is equal to this. Maybe we go ahead and go to the next step now. What are we going to have to do at the last part? At what instant is this force 0? Maybe we need to... Let's completely solve out the problem then. So let's take that answer and say we can find the electric fields. What do I need to do to find the electric field? What do I divide by?
2 pi r1.
2 pi times r of the bigger circle now, r1, because that's the place where we're finding the electric fields. And that's going to be our electric field, right? And then we can skip another step if we want to now, because we can take the value of the electric field here and say that this can give us force if we just multiply by the EMF, or sorry, the electron charge. So the electric force is going to be equal to E times E. We'll do the direction at the end. The direction is going to be easy for us to figure out, kind of. It's actually not that easy in this case. So Fe is E times E, so it's going to be E times this, right? So we take E over 2 pi r 1 times pi big R squared times 6t squared minus 8t. And now we basically have an expression for the force as a function of time on this particle. Of course, since the particle is going to move, this is only good for this moment in time. All right. So now we can plug in values. So F sub E, the electric force, is equal to, electron charge is 1.6 times 10 to the negative 19 coulomb, divided by 2 pi r1. R1 was equal to 5 cm, so 0.05 meters, times pi. Big R squared is 2.5, so 0.025 meters squared, times 6 times 2 seconds squared minus 8 times 2 seconds, because we're finding the force on the, where is it? The direction of the, so when t equal to 2 seconds, calculate the magnitude and direction of the force on an electron located at P1, which is there. Okay, so there we go. And of course, whatever all of this is in Teslas, so we're not going to worry about these seconds right here. This is all just going to be in Teslas. You can figure out what the units need to be. 8 needs to have units of what? Teslas per second. This has to have units of Teslas per second squared. You know what? Let's just do that. Just because the problem was too lazy to put this stuff in doesn't mean we don't have to. This would have to have units of 8 Teslas per second, and this would have to have units of 6 Teslas per second squared. So you get Teslas out of here, basically. Those are just units, though. All right, so what do you get if you calculate out this whole long expression?
8 to the negative 21st.
Yeah, there's someone at my door right now. Hello? I'm gonna go answer real quick.
Pizza guy.
I wish.
I got 2.5 times 10 to
What's up?
negative 21.
I'm going around doing the service audit.
Okay.
Just going around see if you guys need any TV, internet, or phone service at the moment.
I'm good. I'm also working right now. So I can't.
Can I give you a card on the flyer just in case?
I already have Cox.
You have Cox?
Am I not listening?
AT&T?
Huh?
Maybe AT&T?
I have Cox Business. I don't know if that matters.
Oh.
Have a good evening. All right. Sorry about that. They're trying to sell me the same internet that I already have.
Oh.
Okay. So, you said you got an answer. What was it?
We got 2 differing answers.
Oh, okay. Okay.
Oh, wait, 8. Yeah, did you get 8 times 10 to negative 21?
Yeah, that's what I got.
Yeah, okay.
I think that's the right answer. Okay, so you get 8 times 10 to the negative 21. I could check my notes from last year. And the units are obviously going to be in newtons. They should be in newtons. We can check to see if you actually get newtons out of this. Tesla, meters squared divided by meters is just meters. So you have a Tesla times a meter times a coulomb. You know, I guess it works out. Do you all want to work out the units? Tesla,
I got the same answer too.
meter,
Yeah, 8.
coulomb. Is that right? Meters squared. Did I leave any units out?
No, that's right, yeah.
So Tesla we get from this equation. Tesla is basically B is equal to F over QV. So we can replace Tesla with Newton divided by meter per second times Coulomb. It looks like I'm getting Newton seconds, right?
Yeah.
Oh. It's because we did DDT right here, right? So technically, the units on these shouldn't be Tesla per second squared. It should be Tesla per second cubed. And Tesla, you know what I mean? Like, this should actually have a per second right here.
Mhm.
Because when you do DDT, this has seconds in it, basically, right? Or inverse seconds.
Yeah, inverse second.
This is like dividing by time. So
Yeah,
this
it's a
would
rate of
have been
change.
Tesla, but the units of this thing are going to be Teslas per second, basically. So just I'm just going to go back and fix my units here, because this should have been a 3, and this should be squared, and then it'll work out. Anyway, okay, it's good. Always good to check your units to make sure you're not doing something that's silly, like I was doing there. Okay, so that's the size of the force. I think we have time to finish this problem before we go on break, right? Yeah, we can finish this. So that's the size of the force. The next thing we want to do, does anyone have any questions about that part? Okay. How do we find the direction? How do we find the direction?
Well, I would be like, okay, so if we place like a loop, like a conducting loop at that point, and then see like, and then we would just have to flip the direction because this is an electron.
Mm-hmm. I don't know. What direction do you think it will be then? Suppose
I think it'll be downwards.
So you're saying you want to basically kind of like imagine that there was a current carrying wire right here and figure out the direction of the current, right?
Yeah.
How do we do that? What do we need to know?
Right hand rule.
Mm-hmm. What else do we need to know?
The direction of the magnetic field.
We can see that right here, right?
Yeah, we can see that.
whether or not the magnetic field, the flux is increasing.
Yeah, we need to know if the flux is increasing or
Ah.
decreasing. That's right. How can we figure that out?
The flux is increasing, right, due to the equation we're given per time.
How do you know?
We could take derivatives.
Yeah,
Mm-hmm.
Yeah, we could do like the second, or not.
we just
We
need the
can
first.
set the derivative equal to 0, right?
Don't we just need the first derivative? Doesn't it tell you like if it's
Yeah.
increasing or decreasing?
So 6t squared minus 8t, set that equal to 0 and solve for.
No, we don't even need to do that. We just
Yeah,
need
it's
to
already came
know.
up.
We just need to know if this is positive or negative. Right.
It'd always be positive.
Yeah, it'll always be positive.
Well, it won't always be positive. The time is going to change whether it's positive or negative, right?
Mm-hmm.
Mm-hmm.
Okay. I'm sure if the time is between 0 and 1, that this might actually be a negative number. But at t equal to 2 seconds, it looks like a positive number to me. 24 minus 16?
Yeah.
It's positive, right? So this is greater than 0. That means that... and remember, this is the d phi dt. That means the flux is increasing, which means the induced EMF has to point opposite, or has to create a this is what would happen. I'll just put it this way. This is the direction that current's going to have to go, right?
Yep.
Okay. And if the current's going that way, then as I think Cam said, the direction of the force on the electron is going to be this way. Right? Okay. All right, so last part is to find at what instant is this force equal to 0. And for that, I think we can do what you all said, which is we just need to set this equal to 0 and figure out what time this becomes 0, right? Because then the force would be 0. That's the only way it can become 0 is if this thing is 0, right?
True.
Eight over 6 is 4/3, isn't it?
Mm-hmm.
Does that look right?
Yeah.
So at t equal to 0 and at t equal to 1.33 seconds, the force on the electron would be 0. Now, it's it's kind of like, I guess that's true. I was going to say, like, if the magnetic field is changing in time and you get a changing flux and that produces an electric field here, the electron isn't really going to be here at that moment in time. You know what I mean? Like, it's going to move. Would you all agree? Like,
I'm sorry, can you repeat that?
well, I mean, if this particle is subjected to a force at 2 seconds, it's also going to be subjected to a force at 1 second, right? So it's going to move around, is all I'm saying. Like, the electron's not just going to be at this one location, like vibrating back and forth. It's going to be moving. It's going to be, at t equal to 0.1 seconds, there's going to be a force, and it's going to start moving. And now that it's moving, it's going to feel another force because it's going to be farther away, probably. And anyway, I'm just saying. I mean, they did specifically ask the direction of the force at t equal to 2 seconds. So you could say at t equal to 2 seconds, there's an electron there, find the force, right? But that's it. Okay, so that's kind of the end of the discussion of how you find the electric fields when you know that there's a changing magnetic flux. That's really all we were trying to do is, when I have a change in magnetic flux, how do I find the electric field? And that's what we've done. So we have some really powerful ideas that we've developed now in terms of our ability to understand how objects operate, how things move when you're talking about electricity and magnetism. And we started with just little particles of charge. We realized they produce electric fields, and then we figured out that if those electric fields move in time, you can produce what's called an electric current, and we can do all kinds of things that are interesting with electric currents. But then we found that these electric currents also produce these magnetic fields, that once you have a magnetic field or a magnet, you can actually reverse the whole effect and take that magnetic field and move it and produce currents. And kind of that's where we are right now. So the next thing we'll do in the next hour is we're going to kind of bring everything together with Maxwell's equations. We're just going to kind of write all of them down, talk about how they interact with each other. We're not going to solve them, which is what we'll do in a couple weeks, but we will kind of describe the solution that they kind of hint at. So that's what we'll do in the next hour. Let's take a break until whatever 10 minutes from now is, so till 3:10.